Okay, continuing with 7.8 part 2, we're looking at these other indeterminate forms, 0 to the 0, infinity to the 0, 1 to the infinity. And the problem is, immediately, you can see we don't have a fraction of 0 over 0 or infinity over infinity. L'Hopital's rule requires we need a fraction. So let's go through a three-step process to see what's got to happen. You start off with f of x raised to the g of x, of course. One of the most powerful uses of logarithms is that when you have a logarithm of f of x to the g of x, you can bring that power down. So let's take a natural log of both sides here so that we could drop down our g of x. Once you do that, it's just like going back to example 5. You'll probably have 0 times infinity or something like that, with the hopes of then taking this form and rewriting it as a fraction. Once you evaluate what this limit is, we can see very quickly that, remember, we found what the natural log of y is. If the natural log of y is equal to some fixed number like 5 or whatever it may be, we'll call it L, use the property or the definition of logarithms, or exponentiate both sides, e to both powers, and you'll be left with e to the L power. If you had infinity, e to the infinite power would yield infinity. E to the negative infinity, if you think about just the graph of what e to the x looks like, if you had negative infinity over here, e to the negative infinity, of course, is 0. Well, let's go ahead and take a look at some problems and see how we can proceed. Take a look at number 6. If you substitute in a 0, e to the 0 is very close to 1 here, as it's a limit. 1 minus 1 would be 0 itself, and then we'd be raising that up to the 0 power. So at this point, we can realize that this is indeterminate, and I'm going to let y equal this limit. This is really looking at this as if it was step number 1 in our notes at the top of the page. But of course, what we'd really like to do is take a natural log of both sides. If you get one of those forms that were at the top of the notes, let's just change this to write it as a natural log on the left and a natural log on the right. Now what I'm going to do, of course, is bring the natural log inside the limit. I'm going to continue just working through with the limit right here. We'll have the limit as x approaches 0 from the right. Right now I can drop down that x, and it's x times the natural log of e to the x minus 1. If I were to substitute in that 0, though, out in front I'd have 0 with my x. Inside, e to the 0 is 1, and 1 minus 1 would be 0. But again, we'd be just a little bit bigger than 0, because 0 from the right, e to the 0, would be just a tad bit bigger than 1. Suffice it to say, this altered form, this indeterminate form, would be 0 times negative infinity. And again, this is very much like example 5 if we went back to our first video. Well, of course, what we'd like to do ideally is write this as a fraction. Why are we writing this as a fraction? Well, my goodness, that's where we can use L'Hopital's rule. We always need that fraction form. And then let's go ahead and take L'Hopital's rule if it is applicable. Let's first check and make sure it is. Plug in a 0, e to the 0, like we said, a little bit bigger than 1. 1 minus 1 is 0, a little bit bigger than 0. Natural log of 0, we'd see that this is negative infinity up on top. Down below would get positive infinity. We can use L'Hopital's rule here, thank goodness. So what we'll do real quickly is get a little bit messy of a derivative. Up on top, we'll have 1 over e to the x plus 1. You know what? I'm going to recopy this up here just for some space. We'll say we'll get the limit as x approaches 0 from the right. We'll have 1 over e to the x minus 1. The derivative of the inside is e to the x, so tell you what, we might as well just put e to the x all the way up here. Down below, the derivative of 1 over x, we've talked about that before, is negative 1 all over x squared. Right now, we could real quickly make a quick adjustment and see that if we're dividing by a fraction, we're really multiplying through by its reciprocal. So, just continuing some work up here just so that we can see it, we'd have e to the x all over e to the x minus 1 times a negative x squared all over 1. So we'd have negative x squared e to the x all over e to the x minus 1. Well, looking at this once again, you can see sadly we're not able to get a definite value yet. We still have 0 over 0 when we plug in. E to the 0 is 1. So let's do yet again another L'Hopital's rule. This is a very involved problem, of course. Down below, the derivative plain and simply will be e to the x. The derivative of 1 just goes away. And the good news is, if you look down below, e to the 0 is a 1. So I'm not going to have something indeterminate in the denominator. As we look up on top, as we take the derivative, you know what? We're going to need to use the product rule. The derivative of e to the x is e to the x. The derivative of negative x squared is negative 2x. And thankfully, as we work this out, as I plug in a 0, like I said, the top, 0 is going to wind up working out in both of these parts. Down below, I have 1, so we have 0. It's very tempting to say that our final answer is 0. However, what I really want to warn you about, and this is step 3 in our notes, is what you just found is the natural log of y. Y was the original problem itself. But remember earlier we took a natural log of both sides. So what you now know is the natural log of y, this whole limit here, is really 0. So what is y itself, the original limit? We can exponentiate both sides or do a little log circle and get y is equal to e to the 0, which is 1. So our final answer would be a 1. Let's take a look at number 7 real quickly. Plug in 0 from the right. The inside of the parentheses is going to 1. Cotangent. If you looked at the graph of cotangent, hopefully you remember it looks something like so. And we'd see as 0 is approached from the right, we'd be going towards infinity. Again, it looks like we'd have 1 raised to the infinite power. So let's call y our original problem. And from here, we can go ahead and take a natural log on both sides. The reason why we're taking a natural log is so that we can drop a power down. And that's going to allow us to have something more like example 5 that we saw at the very end of that last video, meaning that we're closer to writing this limit as a fraction. That's our ultimate goal. And real quickly, what we can see again is, the cotangent right here, as we approach 0 from the right, this is going towards positive infinity. Natural log of 2x plus 1, well, that would collapse to natural log of 1. This is really in a power struggle, if you would, of infinity times 0. Well, look, another way to look at cotangent is to see it as 1 over tangent. And if we did that, in other words, divide by its reciprocal, this might just wind up being a tad bit more helpful. Because when we rewrite it in this form, you can see really quickly that we will now have 0 over 0, meaning we can do L'Hopital's rule, which is our ultimate goal. The derivative of our top is going to be 1 over 2x plus 1 times the derivative of the inside, so that's going to be a 2 times 1 over 2x plus 1. Down below, the derivative of tangent is secant squared. And thankfully, what you're going to see is even directly plugging in a 0, secant of 0 is going to be a 1. 2x times 0 goes away. The only thing we're left with actually is a 2. But again, please understand what we have to realize is the natural log of y is equal to 2. Remember, that's what we just found right here. Y was the original problem, so y would have to be e to the second, e squared. One final form here, last problem, is infinity minus infinity. Infinity minus infinity is not 0 necessarily. We have to be very, very careful here. And what we need to do quickly is to arrive at a way to attack this problem using L'Hopital's rule. Using L'Hopital's rule, of course, means that we'd like to have a ratio of functions. Now, if I plugged in 0 from, this looks like it's from the left, 1 over x, the Kung Fu Fighter graph, if I plug that in from the left, looks like we'd have negative infinity here. If we looked at the sine wave, as I approached 0 from the left, we'd get something negative. You can see this is my graph of sine. I am approaching 0 from the left side, but it's a negative value. And 1 over that is going to be 1 over something negative small. This works out to something positive then. So this is like negative infinity plus infinity, or infinity minus infinity. Suffice it to say, what we need to do is get a common denominator. What's driving this whole lesson is we need to have fractional forms to be able to use L'Hopital's rule. Getting a common denominator, I think we could quickly see that thankfully this becomes sine of x minus x all over x sine of x. And if we were to plug in 0 now, we'd have 0 minus 0 up on top. Down below, we'd also have a 0, meaning we can use L'Hopital's rule. L'Hopital's rule is going to allow us then, using the product rule down below, the derivative of sine is cosine. The derivative of x is just 1. So that's our product rule right there. Up on top, the derivative of sine is cosine, and the derivative of x is simply a 1. So this might seem to be very promising. I'm sad to say, though, that it's still indeterminate. Plug in 0, you get cosine of 0 is 1. 1 minus 1 is 0. And down below, we'd have 0 just as well. So let's do L'Hopital's rule yet again. The derivative of cosine is sine. And down below, using the product rule, well, the derivative of cosine is negative sine. The derivative of x is 1. The derivative of sine, of course, is cosine over here. And, what we have in this final answer, thankfully, is not something indeterminate. We'll get 0 all over 2, which is just 0, which would be our final answer. Because cosine of 0 is a 1, and we'd get 1 plus 1 down below. So that's how we use L'Hopital's rule to help out with limits.